So my name is Dr. Jenny Koenig, and I'm going to be talking about trying to move towards a more inclusive pharmacology education by reducing the maths gap. So what do I mean by maths gap? Why maths? So maths underpins so much of pharmacology. Let's start with this idea of number sense. Number sense is this idea that you know if you see the number 5 and the number 3, you instinctively know that 5 is bigger or more than 3. And this idea of number sense, when we start to write numbers in index notation, number sense starts to evaporate. And certainly when we write numbers in negative powers, a certain group of students will struggle to really be able to relate that to a size or scale. And we need to work hard to help them make that connection with microorganisms or size of biological organisms. Certainly when we move on to logarithms, we lose a lot of students. And that's unfortunate because many of our parameters, PKD, PEC50 for example, based around this idea of logarithms. Prefixes and units are related to index notation, and there are a number of misconceptions around them amongst some students. Multiplicative reasoning is another area of maths that's really core to pharmacology. It underpins the ideas of ratio and proportion, and that's important for calculating, for example, concentrations and dilutions. But the ability to reason with ratio is really key. Logarithmic scales are a way of sort of representing, sort of increasing by multiples, obviously relates to logarithms and exponential growth. The other core area of maths is what I like to call describing relationships between variables. It's what you might call algebra. I don't like to call it that because it has awful connotations of manipulating symbols on a page for no obvious reason. And really what we're doing in biology is we're using equations and formulas to show how things relate, how one thing relates to something else in a more quantitative manner. So particularly rates of change are important, and that leads on to ideas of exponential equations, which obviously relates to exponential growth and decay. And then finally, the idea of a mathematical model. So a lot of what we do in pharmacodynamics and pharmacokinetics is to talk about mathematical models. So where does the maths gap come from? So there's a lot of aspects to this maths gap, and it arises for a lot of different reasons. So the first reference there I think is a really nice, very concise review of some of the key points around racial equity in maths education. But just to take a few examples, there's the issue of deficit narratives around particularly black students and their alleged inability to do maths, which is unjustified. There's the issue of microaggressions in the classroom. There's different expectations for certainly Asian and white students compared with other ethnic groups. So there's maths education is not colorblind. There's a lot in there that needs to be worked on, I think. The other area that applies to disadvantaged students more generally is the problem of maths teacher shortages. So students who are attending the more disadvantaged schools are hit hardest. And certainly I taught for a couple of years in a large comprehensive school. It was just a bit below average school. And even there we found, this is in England, we found some big problems with finding enough maths teachers, enough teachers who were trained in teaching maths. And then finally, the issue of poor mental health and indeed physical health through childhood. So there's a number of studies that have shown that if students have struggled with poor mental health through their childhood, they fall behind in maths. And I taught maths for a couple of years for a charity for students with mental health issues, and I certainly saw this firsthand, where these students had gaps in their knowledge, gaps in their education. And that meant that then when they got on into secondary education or into university, there were whole areas of maths that they hadn't really covered properly. And that really put them at a big disadvantage. So what I want to try and do is convince you that we need to take these students into account. We need to think about where they're coming from and adjust our teaching so that we make our degree courses inclusive as much as possible. So what is the maths gap? Can we describe it a bit better? So if we take this idea of number sense, then there will be a small proportion of students who will struggle with index notation, and particular negative powers. So I've found that a small proportion, maybe 10% or so of students, will need some sort of help in relating numbers written in this way to size and scale. Logarithms, at least in the UK, is not covered until the final year of secondary school if you do A-level maths. So talking about logarithms is going to be really problematic for the majority of students doing biological sciences degrees. And that's a problem if we're going to be talking about PKDs and PEC50s. So we really need to address that. And I'd argue that if you want to talk about PKD or PEC50, you really need to teach about what logarithms are. I think addressing some of the misconceptions around prefixes is relatively straightforward and easy to do. The ideas of multiplicative reasoning, a lot of the pedagogy around teaching ratio has improved over the last 10-20 years. There are a lot of good ways of scaffolding ratio calculations and ratio reasoning, and I think we should be more aware of those approaches. Particularly because calculating concentrations and dose rates and so on is so fundamental. Logarithmic scales, at least in England, with the latest curriculum reform in 2014, there's a much greater proportion of time devoted to logarithmic scales. So I think the students coming through now are generally speaking more confident in that. That's not so much of an issue, at least in England anymore. And exponential growth. So the ideas of exponential growth really are not covered particularly well, even in the science curriculum. And then finally, if we're looking at formulas and equations, if you take the average university with the average biological sciences degree course and the average student, the likelihood is that they are not able to rearrange equations. So if that's something that you think is important for them, then it's something that I would argue you should be trying to address in your teaching. Particularly when it comes to exponential equations. So that's an area where, unless you've really done A-level maths, final year of secondary maths, you really won't have done that much at all. And certainly the idea of a mathematical model as applied to a biological system is not addressed at school. So when we're talking about Schuld plots, Schuld equations, pharmacokinetics, we really need to be explicit in saying what we mean by a mathematical model and how that sort of abstractive process is done. Which moves me on to teaching about mathematical models, and this is something I've done for many, 15 years or so. And I'm just taking the example of pharmacokinetics for the moment. And I think to make it accessible to a wide range of students, we need to take a sort of multimodal approach. So I like to start with sort of the diagrammatic representation. So here we've got like a one compartment model. So we have we build up a mental picture, a mental model of what we're dealing with here, and being explicit about how we're simplifying a complex biological system into a simpler system. Then when we've got that, we can build up using graphs, both on a linear and logarithmic scale. We can build up an intuitive sense of what's going on in this simplified model. And only then we can then start to introduce the symbols, explain what E is. Most students in the English education system will not have covered E. They won't know what it is. So we can tie all of these approaches together with a verbal narrative, a verbal explanation, and show students how these different ways of getting at this mathematical model, how they can sort of work together. I'm not the only one who thinks modelling is important. So the Vision and Change report from the AAAS 10 years ago talks about this being such an important basic skill in describing biological systems. Biologists should understand the advantages and limitations of these reductionist or systems approaches. So yeah, so I'm not the only one who thinks this is important. So what does an inclusive pharmacology education look like? Well, I would argue that it's one that meets the learning demand by putting in place a way of ensuring that students have the appropriate background knowledge in maths. So we should have a good sense of what they know and can do, or are likely to know and can do, and then put some teaching and learning in place to fill any gaps that they might have. And also provide a variety of ways of representing mathematical models so they're accessible to students with all sorts of mathematical backgrounds. We should also take into account effective demand, and I haven't really talked about that much at all today, but it's very important. I think we need to provide ways of enhancing intrinsic and extrinsic motivation. Some of that is just done by the fact that we're talking about maths in a biological context. And we need to build on their existing understanding, take them from where they are to where we want them to be. And that is the way to build their confidence and to alleviate the anxiety.